Hello everybody, Hobo here, and today again we will be discussing the area of a circle. So we have a circle, and we wish to find the area, and we embed it in a polar coordinate plane. So what this means is that we have it in the variables r, that should be a lowercase r, theta. And we have that the radius of our actual circle that we're trying to calculate the area of is equal to big R. So now, what we will do in this video is we will define a sector element, and then we will doubly integrate over that sector element to calculate our area. So just as we defined the arc element in the last video, we had the infinitesimally small arc ds. So ds is equal to r d theta. So that was our arc element, and now you can maybe guess what a sector element is. A sector element is the infinitesimally small section of a circle. So it's an infinitesimally small sector. And how we will accomplish that is by adding up infinitely many arc lengths from r is equal to 0 to r is equal to big R, and we will take this infinitesimally small sector, and we will integrate it from 0 to 2 pi. Now, let us begin. So we want to calculate the area of the infinitesimally small sector. So what we will have to do is we will have to add up an infinite sum of these sectors, of the arcs enclosed in this sector. So how do we do that? Well, the arc is equal to r times d theta, and if we take this arc and we pull it taut into a straight line, and we treat it like we would a rectangle, which we can because it's infinitesimally small, and when we sum up all the infinitesimally small rectangles, they add up pretty well to approximate the entire area. So then we have some dr and r d theta. So when we multiply r d theta times dr to find the area of this rectangle, then we have r d theta dr, or if written in proper order, r dr d theta. And that is the area of any single arc enclosed in our infinitesimally small sector. So now let's add up over each sector, over all the arcs enclosed in the sector. So that's sigma over r dr d theta, and so that accomplishes the finding the area of a infinitesimally small sector. But now we want to find the area of the entire circle. So we'll have to sigma again, because we're adding up each tiny sector, and the limits over here will be 0 to 2 pi, and the limits over here, which is the variable r, will be 0 to big R, because that's we take the arc lengths going from 0 to big R. And now we have a double infinite sum of infinitesimally small components, which is, as defined, a double integral. So if we write out this double integral, I'll erase our picture here. If we write out this double integral, we have integral 0 to 2 pi times 0 to r of r dr d theta. So if we integrate if we integrate over the variable r first, then we have integral r dr from 0 to r is equal to half times r squared, big R squared, and then we plug that in, and then we have left integral 0 to 2 pi times, and then we can pull out this half r squared because it's a constant. So half r squared multiplied by the integral 0 to 2 pi of d theta. And integral 0 to 2 pi d theta is simply theta. So then we're left with half, yes, integral 0 to 2 pi d theta is 2 pi because it's theta. So half times r squared times 2 pi. And the half and the 2 cancel out, and we're left with pi r squared. Thank you very much.